Okay, let's just go over the problem for a minute here. Suppose you have a window on a computer and you're increasing its size in this direction, let's say. Initially, the window is 3 by 6 centimeters. 3 by 6 centimeters. And you're increasing it in such a way that the height changes at 2 centimeters per second, constant rates, and the width at 4 centimeters per second. So the window is getting bigger this way. The question I'm asking in one is, how fast is the area of the window changing at the moment when the width is 19? So at some moment in time, the width is 19. Now the area is going to be increasing all the time. Of course, it's getting bigger, but at each moment in time, I would like to know at what rate is this area increasing. Now, maybe this area is not changing at a constant rate. We'll find out that it is not changing at a constant rate, that in fact, as it gets bigger, the rate at which the area changes is also increasing. So that's the first question is at what is the rate of the area of the window changing at the moment when the width is 19? Second question, how fast is that same window changing, the area of the window, at the moment when the window is square? So presumably at some moment the window will be square. I don't even know what time that is, or if that even happens, but we'll see that it does. Eventually the width overtakes the height and at some point becomes square. After all, the width is increasing at a faster rate. So let's look at the solution. Now, part of the solution of a related rates problem is to set up proper notation and identify the quantities whose rates are known and the quantities whose rates are unknown. So what about known? That's the height and the width, of course. So let's let Wt equal the width at time t, and h of t equal the height at time t. These rates are known. So I write that this way. The derivative of the rate of change of the width is constant at 4 centimeters per second. The rate of change of the height is 2 centimeters per second. These are the quantities whose rates are known. The quantity whose rate is unknown is the area. So let's let AT equal the area of the rectangle at time t. We seek 8. Let's put the question mathematically now. It's important to do that. We seek A prime t when Wt equals 19. All right. The idea in a related rates problem is to begin with the quantity whose rate is unknown and the quantities whose rates are known to find an equation relating the two quantities. Equation relating the known and unknown quantities. Because the idea is that we'll differentiate and therefore get an equation relating the known and unknown rates. Well, what is that? I've got A of t here. Well, we know that the area is the width times the height. Now this is true at all times t. At any given times t, the area is equal to the width at that time, times the height at that time. The idea in a related rates problem is to now differentiate that equation with respect to time. A related relates problem typically occurs in time, and that's always the variable of, with which we are differentiating, with respect to which we are differentiating. So let's find a prime t. We know that a of t is w of t times h of t. Let's differentiate a prime t. Well, here I have a product of two functions, wt times h of t. So naturally I want to use the product rule. Derivative of the first times the second function plus first function times the derivative of the second. That gives me an equation relating the unknown rate, that's a prime t, with the known rates, that's this rate and this rate. So let's write in right now what those rates are. Remember it was 4 h of t, so the unknown rate a prime t is 4 times h of t plus wt times 2. So once again, we seek a prime t when the width is 19. Well, that's fine. I could put 19 right in here right now. The only problem with that is I don't know what the height is at that time. So that's our problem now. What is h of t when wt equals 19? How do I solve that problem? Well, what I'm going to do is find out the moment in time when the width is 19. So let's see. The width is initially 3, and it's increasing 4 centimeters every second. So that's the equation of the width in time. Notice, for instance, W0 is 3, and at 1 second, it increases by 4 centimeters after every second, so it's therefore, in this case, 7. The width is 7 centimeters 1 second later. And likewise, h of t can be determined easily. It's 2 plus 6t. Oh, excuse me, no, it's not. Got those backwards. It's 6 is the initial plus 2t, right? Well, what I'm thinking is that if I could determine the time when this quantity is 19, I could use that time to evaluate using this equation, the height. So let's do that. Solve 3 plus 4t equals 19 for t. That's not so hard. Subtract 3, 4t equals minus 19 minus 3, 16. That gives t equals 16 over 4 equals 4 seconds. At 4 seconds, the width is 19. W4 is 19. Well, what's h at that same time? H at 4, remember that's 6 plus 2 times 4, 2 times 4, excuse me. Oops. Oh, what happened? What happened? Oh, okay. All right, little mix up there. Okay, W of 4 is 19. What's H of 4? That's 6 plus 2 times 4 equals 14. Good, let's go back to our formula to remember what that was. for A prime t. We found that by differentiating right here. Let's use that. Remember, A prime t was equal to 4 times h of t plus w of t times 2. So when wt is 19, well, we know that that happens at 4 seconds. That's at time 4 seconds. W4 is 19. H of 4 we found out to be, let's go back, see what it was. H4 is 14. Found that to be 14. Therefore, A prime at 4 seconds is equal to 4 times h of 4 plus w at 4 times 2 equals 4 times h of 4, that's 14, plus w of 4, that's 19, times 2 equals, what's that, 56 plus 38 equals 94 centimeters squared per second. Remember the area, that's the units for area, rate of area, centimeters squared per second. We lost the problem there, but that's okay. So let's go on with part 2. Again, I'd like to state the question mathematically. What is A prime t when the rectangle is square? What does that mean? Well, that's when W of t equals H of t. Well, remember we had formulas for WT and H of t. What were they? They were 4 plus, no, it wasn't that, excuse me, it was the initial, remember it was 3 plus 4t equals 6 plus 2t. So can we solve for t here? Let's subtract 3 from both sides. So 4t equals 6 minus 3 plus 2t. 4t equals 3 plus 2t. Let's subtract 2t from that side. 2t equals 3. Divide by 2, we got t equals 3 halves, or a second and a half. At that time, 1.5 seconds, we find that the width and the height are equal. The rectangle is square at a second and a half. So again, we can determine A prime at 3 halves. That's 4 times h at a second and a half plus the width at a second and a half times 2. But what is h at 3 halves? We didn't determine that. H at a second and a half, well, that was 6 plus 2 times a second and a half equals 6 plus 3 equals 9. Likewise, the width must be 9 at that time, 9 centimeters, because the window is square at that time. That's the time when the width and the height are equal. So therefore, our final calculation, the area at a second and a half is 4 times 9 plus 9 times 2 equals 36 plus 18 equals 54 centimeters squared per second. That's the rate at which the area is changing at a second and a half. Notice it's less than the rate at which the area was changing at 4 seconds. That was our answer to part 1. It was, as I recall, let's go back. In part 1, we found our answer to be 94 centimeters squared per second. That was at 4 seconds, I believe. Correct? At a second and a half, we found it to be 54. So you can see that the area is, of course, the rate at which the area is changing is increasing. At a second and a half, it's 54. At 4 seconds, it's even more, it's 94. So that's different from the height and the width. Even though the height and the width are increasing at a constant rate, the area is not.